Lesson 1-4, sketching graphs and comparing functions. When we compare functions, we're going to use the key features to help us compare two separate functions. These are the key features: the domain, which is referring to all the values of x. The range are all the values of f of x, or think of our y coordinate. The intercepts, where is it across the x and y axis? Symmetry, is there symmetry? And if so, is it reflection or is it a rotation? End behavior, where does the graph go when you go to the right or to the left, or as x increases or x decreases? The extrema is looking at the high point and the low point. Increasing or decreasing, looking at where is the line going up, where is the line going down, as is referring to the x coordinates. And then the positive and negative, is it above the x-axis or below the x-axis? So for this one, we are going to sketch a linear function when we are given this information. Not all of the problems are going to give us the same information. We can only do a rough sketch based on the information they give us. So here it says the y-intercept is at 0 and -70. So first off, I have to think of what am I going to count by on my axes so that I can properly graph this. I'm going to count all the axes by negative, or we'll count by 20s. So maybe let's count by 10s. If we count by 10s, this would be 10, 20, 30, 40, 50, 60. This is 70. That means this is -70. This would be 70, and this is -70. So everything's counted by 10s. So our first one, the y-intercept's at 0, -70. So that means I'm going to put a point down here at 0, -70. Linearity just says that it's a straight line. So wherever points I make, that has to be a straight line when I connect them. It's positive for values of x such that x is less than -30. What that is saying that any number less than -30 is above the x-axis. So I can go to -30 on the x-axis, which would be right here. Anything to the left of that point is going to be above the x-axis, and anything below it is going to be it'd be a negative. So it's decreasing for all values of x, which just means as I go from left to right, my line is going down. So for this example, we're going to have actually a negative slope. And then if we look at their end behavior, as x approaches positive infinity, when I go to the right on the x-axis, my line is pointing downward. And as I go to the left on the x-axis, my y is going up, or my y is increasing. So now I can draw my line and connect these 2 points. My line will look something like this. So everything to the left of the x-intercept is above the x-axis, and everything to the right of the x-axis is below the x-axis. Next, let's sketch this one. So we have an x-intercept at 0, 0. It's linearity, it's a linear line. All values of x such that x is greater than 0 is positive. So any number bigger than 0, so to the right of the origin, is going to be above the x-axis. And then our end behavior, as x approaches positive infinity, f of x is positive infinity. As x approaches negative infinity, f of x approaches negative infinity. So I know I have this point right here at the origin. Anything to the right is above the x-axis. Anything to the left of the origin is below the x-axis. So that is just one sample of what we could have. You could also do this. That would work. It's a straight line. It's above the x-axis when it's to the right of 0 and below when it's left of 0. I could also do this as well. So there are infinite amounts you could possibly have. Just as long as we know that it matches this. It's a straight line. When x is greater than 0, it's above the x-axis, and then it follows the end behavior. Moving on to our next example. It says use the key features of the function to sketch this graph. So these are nonlinear, which means they have corners, they got bends, and the line. So the x-intercept is 0, 3. Linearity, nonlinear. It's continuous. That means there's no jumps, breaks. Positive for all values of x. This means that everything is above the x-axis. It's decreasing for all values of x such that x is less than 0. So when x is less than 0, it's going down. The extrema, you have a minimum at 0, 3, so that's the lowest point you possibly have. In the end behavior, when you go to the right or left for x, your f of x or your y is always pointing up. So if I go to 0, 3, put a point here, that means it is going down when I'm less than 0 on the x-axis, and then it's increasing. That means it would increase when it comes up the other direction. So let me fix that one. Since this would be more like a parabola, that would be our graph for here. All of our x's for wherever we plot is always above the x-axis. So that's what it means by positive. We know it's decreasing when it goes from left to right. As long as you get to 0 on the x-axis, which would be right here, anything to the left of this line is going down. Next, let's graph this one. We have an y-intercept at -5, so -1, -2, -3, -4, -5 is right here. It's nonlinear, it's continuous. It's positive for all values of x such that x is less than -3.5. So if it's less than -3.5, and we go to where -3.5 is, -3.5 is right here. So that means it's positive when it's less than that. So that means it has to be above the x-axis here. And it's above the x-axis when x is greater than 1.5. So 1.5 would be right here. That means it's greater than right there. Relative minimum, we have a relative minimum at 1 and -6. So 1 and -6 would be down to here. And it says it's increasing for values of x such that x is greater than 1. So anything greater than 1, it's always increasing. Then the end behavior as x approaches positive infinity, f of x equals positive, is approaching positive infinity, and as x approaches negative infinity, f of x approaches positive infinity. So to draw this one, I would just come down here, it's here, and then it pops back up, and then I would just probably go up this way. And that would be a rough sketch of what that graph would look like. Next, that's a real world function. Here it's working with a word problem. Faye is driving a car. She is thinking of buying. She decides to accelerate to 60 miles per hour and then decelerate to a stop to test its acceleration and brakes. It takes her 15 seconds to reach her maximum speed and 15 additional seconds to come to a stop. Use the key features to sketch a graph that shows the speed y as a function of time x. So here we have the information with our key features that we're going to use to graph. First thing I want to do is just label my axes. I'm going to go from my x's to 0 to 30, so I'm going to count by threes. So this is 3, 6, 9, 12, 15, 18, 21, 24, 27, and 30. And then I count by sixes on my x-axis, or my y-axis. 12, 18, 21, actually 6, 12, 18, 24, 30, 36, 42, 48, 54, and then 60. Says height starts her test drive at a speed of 0 miles per hour. So that means I would have a point at 0, 0. Because remember, our time is here and our distance is here. So that's 20, that'd be 0 miles per hour. Or this would be our speed. And then it says it's a function that models a situation is nonlinear, so it's not a straight line. The extrema maximum speed is 60 miles per hour, which she reaches at 15 seconds into her test drive. If I go to 15, I'll get to 60. That would be here. So I have a maximum up here. It's increasing. Her speed increases at a uniform rate for the first 15 seconds. So from 0 to here, it's the same speed. So it's a straight line there. It's decreasing the speed at a uniform rate for the next 15 seconds until she reaches a stop. If I go back down for the next 15, that means I'm going to have a point here at 30 seconds. So that means I can go down here, and that's where it would end there. Because A starts at 0 miles per hour and ends at 0 miles per hour, there is no end behavior because that wouldn't make sense going to negative infinity. So that would be the rough estimate or rough graph of the situation that we were just presented with. Next, Alicia talks each morning before school. An app on her phone records her pace over the course of her 40-minute jog. Use the key features of her jog to set the graph of the function. So here we have our y-intercept. Alicia's starting pace is at 0 miles per hour. The extrema, her fastest pace is 6 miles per hour. It occurs from the 20th to the 35th minute. Alicia's pace is increasing from 0 to 20 minutes. It's decreasing, and she's getting slower from 35 to 40 minutes. The end behavior, Alicia starts jogging at 0 minutes and stops at 40 minutes. So now let's go to our coordinate plane so we can graph them. To our axes, we're going to have the x-axis as time, and our y-axis is going to be the pace. We're going to label our axes now. So we're going to count by fives for the time. Let's be 5, 10, 15, 20, 25, 30, 35, 40, 45, and then this last one is 50. And then we're going to count by ones here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So it says her starting pace is 0 miles per hour. So we're starting here at the origin. Alicia's fastest pace, 6 miles per hour, occurs from the 20th to the 35th minute of her jog. So if I go to 20 and then 6, 20 and 6 would be here. And then 35 and 6 would be here. That means she stays at that same pace from this point to this point. So that's the maximum pace that she goes, or fastest she goes. It's increasing for the first 20 minutes. That means from 0 to 20, she's increasing her pace. Then decreasing from 35 to 40. 35 to 40 would be mark would be here, so she is going down from here down to here. So let me do a better line. And that would be a rough sketch of what her pace would look like if you were to graph the data from her phone. Next, example 4, compare the properties of linear functions. So it says use the table and the graph to compare the two functions. So these are two separate functions, but they're shown, the data is shown in a little bit different way, one in a table and one as a graph, and we want to compare the two functions, and we're going to use the key features to do that. So right now we could say, like if we were to draw this, the table 1 on here, let's do that. So -2, -6. -2, -6 would be roughly here. And then we'd have -1, -4. And we'd have 0, -2. And we would have 1, 0. And we would have 2, 2. Which our line would look like this. Now we can compare the two. And we have some statements on the next slide that we can use for that one. It says which statements about f of x and g of x are true? Select all that apply. The letter A says g of x has a faster rate of change than f of x. So if we go back, g of x, or f of x, we would say this is going up 2 over 1. So this one has a slope of 2. And the other one is going to have, it goes down 1 over 2. So this would be 1 out of 2 for g of x. So we would say f of x has a greater one than g of x. So this first statement, g of x is a faster, that is not true. The x-intercept of g of x is greater than the x-intercept of f of x. So if we go back to our graphs here, f of x is at 1, g of x is at 1, 2, 3, 4. So g of x has a greater x-intercept. G of x is greater, so we would say B works. The y-intercept of f of x is greater than the x-intercept of g of x. So we go back to that, so the y-intercept of f of x. That means the red one, y-intercept's at -2. The x-intercept of g of x is still 1, 2, 3, 4. So no, that is not true. So C is not true. Both functions are decreasing. We know one's positive, one's negative, so they are not. E, f of x increases while g of x decreases. So f of x, the red line was going up, the blue line was going down, so E would be correct. And then letter F, f of x has a faster rate of change than g of x, which is true. That's just the opposite of what letter A is saying, and that's what we found. F of x was 2, g of x was 1/2. Another one, it says use the table and graph to compare these two functions. Again, we're going to graph the two on the same coordinate plane, so then you can compare it a little bit easier. So we have -3, -6, -3. -6 will break over here down to -3. -3, -2. 0, -1. 3, 0. And 6, 1, which would be roughly here. Our line would look something similar to this. Now this one does not have choices, so we can just pick a few key features to compare. So the x-intercept for f of x is 3, and the x-intercept for g of x is -2. So we could say g of x has greater x-intercept than g of x. Actually, no, f of x, sorry. So f of x has bigger than g of x. So this red one, this one is f of x. If we were to compare the y-intercepts, we have a y-intercept up here and y-intercept right there. So g of x has greater y-intercept than f of x. And we could also say both functions are increasing. Now there are a couple other ones you could talk about, like the rate, if you wanted to, but a few statements to do the comparison would be appropriate. Next, these says use the table and description to compare the two functions. So we have f of x and then we have g of x. G of x has a slope of -4, which just means the line is going down from left to right, and it goes through the point 0, -3, which this is the y-intercept, and -3/4 and 0, which this would be our x-intercept. Over here, this is our x-intercept. Here's our y-intercept. We could find the slope, let's just do the comparison with the x and y-intercepts. So the g of x has a x-intercept of -3/4, and f of x has -4. So we could say g of x has a greater x-intercept than f of x. And then we could say they both have the same y-intercept. Now, if you want to do more comparison, you could graph both of them on the same coordinate plane. But for this lesson in particular, two statements like this is good enough for the comparison. Let's examine categories to see how to use description in the graph to identify key features of each function, then complete the statements to compare the two functions. So if we look at the one on the right, the g of x, we have a minimum down here, which that would be a little bit less than -1. We have a relative max, which would be roughly 1, 2, 3, 4, a little bit over 4. You can see the relative minimum for f of x is 4.7. So that would be higher than what g of x is. The relative minimum at 1.1, which is also higher than g of x. The end behavior for g of x, you have negative infinity when you go to the left, and then you have positive infinity to the right. And the end behavior for f of x, as you approach negative infinity, when x approaches negative infinity, f of x approaches negative infinity. And as x approaches positive infinity, f of x equaling positive infinity. So the end behaviors are the same. So now if you could compare them side by side here, in a table format, it says the f of x intersects the x-axis once at -3.4. G of x has three x-intercepts, -1, 1, and 2. So we would say that the f of x has a smaller x-intercept compared to g of x. The y-intercept, the f of x intersects at 1.5, g of x is at 4. So g of x has a higher y-intercept. The extrema relative maximum for f of x is 4.7. The relative minimum is 1.1. G of x has a relative maximum of about 4.2 and a relative minimum of about negative 1.2. So f of x has a higher relative max, and g of x has a lower relative minimum. And if you compare the two end behaviors, you can see that they are the same. So some statements. X-intercept of f of x is less than any of the x-intercepts on g of x. The graph of g of x intersects the x-axis more times than f of x. That's a statement you can make. The y-intercept of f of x is less than the y-intercept of g of x. G of x intersects the y-axis at a higher point than f of x. We did the comparison of the relative max and the minimum, and the two functions have the same end behavior as we stated before. Then our very last one, the x-intercept for one function. So we'll call this one g of x. So g of x has x-intercept at 2, 0 and 6, 0. If we put them both on this one, so I would have 2, 0, and we would have 6, 0. We'll put 6 right here. So 6, 0. The y-intercept is at negative 6. Put negative 6 here. Says it has a relative maximum at 4, 2. And it has end behavior as x approaches positive infinity, f of x approaches positive infinity, and as x approaches negative infinity, f of x approaches positive infinity. So that means this one's going to look something similar to this. And so if we were to compare it, the two, g of x has more, actually have the same amount of x-intercepts, but g of x has a higher x-intercept. Y-intercept's negative 6. This one is at 1, 2, 3. So f of x has higher y-intercept. Relative max 4, 2. This one is at negative 1. So this one also has a higher relative max. End behavior is not the same. So we would have the end behavior are in opposites. So we'd say end behavior both are opposites. And that would be enough to do the comparison of our two functions. So that is our lesson on sketching graphs and comparing functions.